This is FloatZone accelerating memory error detection using the floating point unit. Okay, let's start with the basics. What are memory errors? Let's say you have a C application, you have a pointer, it points somewhere, and we want to write to it. The question is, are we about to do something unsafe? There are a bunch of reasons why it could be unsafe. The pointer could be pointing out of bounds, so it's beyond the original buffer it was pointing to. It could point to freed memory. In either of these cases, we probably have a bug in the application, and we maybe even have a security issue because we just silently overwrite random memory. And memory error detection is turning these silent failures into actual errors. So one of the most runtime efficient ways we can do this is using red zones. So in this example, we have a green area. It's 4 bytes of valid memory. And the way red zones work is that we mark the area around it, we reserve it, and we mark it as invalid. The way we mark it as invalid is by putting certain magic numbers in there. In this case, we put 4 times the hex number 8b into the red zone. And what we cannot do to the original code is we can prefix, with the help of the compiler, for example, some code that automatically looks at the address we're about to access and checks if the address points to this red zone byte pattern that we declared as invalid memory. And if it is the red zone byte pattern, then we can say, well, you're most likely accessing invalid memory now. Now, the goal is always to go faster. And the question is, where is the remaining overhead in this still or already very fast solution? And if we benchmark it, we see that most of the overhead comes from these 2 lines at the top. So we load the red zone value, we compare it against the red zone pattern, and then we potentially go to the error handler. Note that the error handler is not part of the overhead. It's really cold code. It's like from millions of checks, maybe it's called once, because most memory accesses are usually valid. So the question is, how can we do better than these 2 lines of code? And if you just look at this code as it's here presented, you probably say that looks pretty much optimal, like it's doing the bare necessities to just compare the red zone value. And you're right. However, the CPU doesn't see this abstract code. It doesn't see the variable and whatnot. It sees instructions. So maybe if you look at the instructions, we see an angle to make this faster. So if we take this to a state-of-the-art compiler and we compile a check, we get these 3 instructions out. We get a load, we get the compare against the red zone value, and then we get a conditional branch to our error handler. And the question is, can we find better instruction than those 3? We're competing against a state-of-the-art compiler. And the angle we try to approach is to say, well, what if we think about what is the optimal way to encode this kind of check? Like, what's the things we want to improve? And we came up with 3 things. One is, modern CPUs are kind of weird. They're super scalar, they're out of order. So there's a bunch of ways you can improve performance by using specific instructions. So for example, you use a part of the CPU that's underutilized. And if you do this, and the part is usually just idling, and you get an instruction running there, you essentially pay very little runtime cost because it's already just idling. We call this usually instruction level parallelism. Another point we want, and this is pretty obvious, we want high throughput instructions. We want to go fast. And the last thing we want to get rid of is the branch predictor mess we have at the end. So we have a branch that goes through very cold code. So there's 2 problems. One problem is it could speculate and say we go to the code, in which case we mispredict, we have to roll back, so that's a performance hit. The other problem is, even if the CPU is really smart and it always predicts this is going, it's not going to be taken, we still spend resources from the branch predictor to predict this branch, and we actually want these resources to be spent on our actual application code. It also has branches, those need to be predicted. And if we mispredict those, we also get a performance hit. So where do we get those magical instructions that hit all these points that we have here? And our approach in FloatZone is essentially we say, well, floating point operations seem like a really good fit. The floating point optimizations run on a part of the CPU that's often relatively idle. FPUs are really fast, and there's quite a few applications that don't really do a lot of FPU work. Think of like web servers. They don't really crunch like floating point numbers the whole day. They do integer stuff. They have strings, which are just integers, and so on. So if we could get floating point instructions, or if we could put this check into floating point instructions, we could use this underutilized FPU that's anyway already running and kind of compute those checks in parallel to the actual workload of our application. The second point is a lot of FPU instructions or floating point instructions are very high throughput, so that's also nice. And the last point with the branch predictor is a bit tricky. So the good news is the FPU can't branch, so it's very easy not to mess with the branch predictor. The bad news is the FPU can't branch, so we can't branch. So if we have this conditional branch at the end, like we can't do it with a FPU. There's no floating point branch instruction. So the solution to this problem we found in a nice book called IEEE 754. You might have read it. It's essentially defining how floating point arithmetic is supposed to work. And for the most part, CPU vendors kind of stick to it. Now, I'm not going to spoil the end, but essentially one point of the book is that there's something called floating point exceptions. You might see them, and essentially the way you look from like a normal user perspective is that you get sig FP, so sig floating point exception. And the nice thing about them is they redirect control flow to the signal handler, but they don't do branching. There's no prediction going on or anything like that. So that seems like a really good fit. But there's actually even better news. Floating point exceptions are essentially control flow that's happening on an operation with specific operands. So if you kind of think about it, it's kind of like a conditional jump we're doing here. And what we're trying to encode is a conditional jump. Conditional jump is if our memory we're trying to access, if that's our red zone value. So if you're trying to, if you try all the possible exceptions, all the different things we could compute on them, maybe we could find like one magic instruction that encodes this whole conditional jump we're trying to encode here. So of course, there's a bunch of different exceptions. There are a whole lot of floating point operations and a whole lot of numbers. So we had to do a bit of math. And I'll leave you the paper for that. And we kind of just skip over to the actual final point. So what we settled on after crunching all the numbers, looking at all the exceptions and all the operations, is FloatZone. So the idea of FloatZone is two parts. The first part is we go to a process, and we can do this per process, and we say, hey, CPU, tell us, please, if we get a floating point underflow. So to be clear, underflow is not like the colloquial negative overflow. It means the floating point number goes so close to 0 it can't be represented by the normal floating point format anymore. We call this subnormal usually. So we do this, and once we do this, the whole check can be encoded in one single instruction. So what this instruction is doing, it's doing a floating point addition, which is good. That's a really fast operation. And it stores the result to some random dead register that we selected. Another interesting part, the floating point addition adds two numbers together. One number is a magic constant that we essentially selected. You have to read the paper how we come up with that. But just think of this as a floating point constant that we found. And we add this floating point constant to the memory that the pointer is pointing to. So the nice thing is this instruction can also directly load the memory that the register is pointing to, because x86 and you encode a lot of stuff in there. All right, so why does this work? If we go back to our starting example, we have valid memory and we have invalid memory. The red zone pattern is pretty much the same. In FloatZone 8B, 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 that's how we designate invalid memory. And let's start with the boring case first. So let's say pointer goes to valid memory. What the check is doing, it takes the floating point constant, it adds the random number that's in memory, and what essentially always happens, because it could be, it's probabilistic, there's like a value that could be a red zone value, but what usually always happens is nothing. It's valid memory, it's supposed to do nothing. But the interesting case is, what if the pointer goes to the red zone? So what now happens, we add the magic constant, and we add the red zone value together. And this happens to be a floating point number that's so close to 0 it can't be represented, but it's not 0. And the FPU notices that. So what the CPU is doing, it creates a floating point exception, and we see it with the sig FP, so our signal handler for the floating point exception. And we just put our error handling code that used to be behind the if, in the if body, we just put this into the floating point exception or the signal handler. We can filter out some false positives, and that's pretty much the whole system. It's pretty simple. So the question is, how much did we gain? Like, we were trying to improve performance. So we took our primitive, so our BADSS, and we built a full sanitize out of that. So it just built on Clang on LVM, and you can just compile normal C programs with that. We run spec on that, and the performance is degraded, or like the performance improved by about 30 to 16%. For spec CPU 2006, the overhead of, compared to the best state-of-the-art solution that we currently know of, is about half. And for fuzzing, the throughput is about 72% higher. That means we run about 72% more executions of the same program because the program itself runs faster. So to summarize, this common pattern of like checking red zone values that a bunch of different memory error detectors employ, we can encode it with the help of floating point operations. The nice benefit of floating point operations is that they, on the first glance, don't seem like actually better, but they have a lot of microarchitectural benefits, things like the branch predictor, instruction level parallelism. And what comes out of that is a memory error detector that's significantly faster than most state-of-the-art solutions, actually all state-of-the-art solutions, I think. And with that, thank you, and let's move on to questions.